Let's discuss a case study involving the normal modes of a disk drive. This was a study of one of the original disk drive models. It was being created in Ann Arbor, Michigan by a fellow named Sam Irwin. He had been a pioneer in the whole business of computing and terminals, smart terminals, and so on, and recognized the need for compact disk drives to fit into PCs. We're going to talk about some of the design considerations here. En route, I want to mention a separate topic called mode tracking, which is important in several technologies. In our case, it's a study of the way that vibration frequencies change as you change a design parameter. There was a model made of a component of the disk drive, namely the read-write arm called the armature arm housing. Then there was a model, a finite element model of the mainframe, and then an assembly study that was done. Finally, I challenged two of my doctoral students to study this same industrial problem as a part of their doctoral dissertations. The sponsor of this project was Irwin International of Ann Arbor, Michigan. The president was Sam Irwin, who had made his fortune in an earlier corporation that made intelligent terminals. Sam sold that company to a larger corporation and was reputed to have made some tens of millions of dollars on that deal. So this was a new venture, and Sam, I think, correctly interpreted the enormous need for disk drives to be put in smaller computers, such as the personal computers. The device that we're going to look at was a 5-inch micro Winchester disk drive that's named after the Winchester disk drive that the IBM Corporation had made. Now, the disk drive is made of several components. When assembled together, it was hoped their lowest frequency would be 500 hertz or higher. This was so that you didn't get some kind of resonance with the drive speed of the disk, and particular with other components such as ball bearings that might give multiple harmonics of that. We spent a fair amount of time looking at the read-write arm called the armature arm, and it's a sort of a truss construction. There's also an aluminum mainframe casting. There is a shaft for the armature arm, and there's a spindle, a disk hub, and the disk itself for the spinning media. Another professor, John Taylor, helped on this project and was instrumental in redesigning the armature arm as a Vierendeel truss. Irwin International had a fast Fourier analyzer, including the crystal hammers that are used to tap a structure and then infer the natural frequencies. Their in-house engineers were electrical engineers, not structural dynamicists. So they really did need a little bit of help on this project, especially interpreting mode shapes. I think they had a pretty good concept about normal mode frequencies, but I think they didn't really understand the normal modes themselves. Particularly, I think boundary conditions were a little bit of a puzzle for them. I can show you one of the disk drives that I picked up from Irwin International. This is one that's a partial assembly. It has the media here, which is a magnetic material that spins. There's a hub that it is clamped to. On the back side, with the spindle protruding through the one side of the casting to the other, is the motor that drives the media. Over here, this nice arm-like thing is being controlled also by a motor, and positions this read-write arm. And it moves in a rotational way rather than translational, which is probably a little more common today. Both are used nowadays. The Winchester heads are not mounted on here. They were spring-loaded and would read both the top and the bottom side of the disk at the same time. The hole that you see here was filled with quite a large air filter, and it turns out that filtering out smoke particles is very important. The Winchester head rides something like 12 microns over the surface of the disc, and a smoke particle can be as high as 15 microns bumping up from the disc if it's stuck there. And that can cause the Winchester head to crash. So there is some worry about keeping that, the bay in which the spinning disc is located, absolutely clean. Here's a cover that will go over the spinning disc area. It's getting a little tarnished now. The final version was an aluminum cover stiffened with some stiffeners embedded in it. And it was decided to make it a structural member as a result of some of our earlier calculations that showed that the system was too flexible. To achieve that, there's a labyrinth groove here for an O-ring that will keep the airtight nature, and then there are bolts that draw this cover down, and you get a hard flush seal metal on metal that provides the structural continuity. Now, in the next two figures, I'm going to discuss design considerations for this disk drive. I sat down and wrote out a few things when we were speaking with Olivetti about using this disk drive in one of their computers. First of all, on the structural performance side, we would like to have good vibration characteristics. That has been printed in red to show that's something that I did work on, as well as the air flow through the system and the air seal. I didn't really work on reliability, stress, fatigue, or corrosion. Those were going to be probably long-term problems, the reliability and corrosion. Stress and fatigue problems were probably not going to occur, although if this were a defense project that many lives depended upon, I think you would probably do more work up front on those things. Here's a small sketch of the body. We now follow up with these topics. The economics of the production of such a device are of course almost overriding in importance. Manufacturing concepts, and that's where it ultimately failed. Maintenance would have been a long-term problem. Making sure there was an adequate supply of electrical components primarily, but also mechanical components. I was made aware that the electrical industry depends so much on their vendors that they require multiple source. I think the automotive companies do as well. Aesthetics. Yes, we want this device not to make a lot of noise and to look reasonably nice, but that's not a big thing. It's hidden inside the computer, and the noise levels were not very bad. As far as safety and pollution, other sorts of things, about the only thing that came up was the danger of the spinning disc throwing pieces off from it. An earlier model had done that when they had weighted it with some lead chunks. But generally speaking, it's confined inside a computer and wouldn't be a danger. It's not so likely that the little disk drive itself would pollute the environment. It's more likely that the environment would pollute it, particularly from smoking. As I mentioned earlier, that is a large hazard for computers, and I believe if any of the viewers do smoke, if you knew how hard it is to keep those smoke particles out and how bad they are, you wouldn't smoke near your disk drive. Earlier I mentioned the concept of mode tracking. That's a fairly important problem in several industries when you're trying to follow the natural frequencies of a system over some parameter range. Now for aircraft, often wind speed is the parameter that's changing. And people like to do ground vibration studies or air off studies and then check those frequencies again as the system is flown 100 miles an hour, 200, 300, and so on. Sometimes what happens to those natural frequencies and the shape of the normal modes can determine whether you get wing flutter or other bad situations. In our problem, we're going to look at the baseline design shown with this bottom set of frequencies. Now the spectrum goes on out to much higher frequencies, but there would be certain frequencies that could be tested with the original design. Now if their design changes, and we did it by stiffening the armature arm in the case of its frequencies, we found that we got another set of frequencies and later another set yet. One thing that's a worry is that the modes will cross, as shown here. I'm mentioning it here in our energy conserving system only because it's a matter of understanding the system. In non-conservative systems with fluid flow over a body, for instance, or with suitable controls that have instabilities, then sometimes these crossings can cause fluttering motion. So one way or the other you want to understand what these mode crossings are. And a way to do that is to make relatively small changes in your parameters so that you get cuts through the frequency spectrum at fine distances. It's possible for one of the lower frequencies, such as this one here, to actually disappear out of the figure. And we do that in our redesign of the armature arm. It's also possible for a higher frequency up here to come clear down and become the lower one and then go back up again. So very important to consider what's going on. Now, one way that's done is to think of the mode shape as a way of describing the mode, not just as frequency. And you can then perhaps do correlations between the perturbed set of frequencies up here and the original baseline ones here. Often people will give names to those modes. In automobile and truck situations, there are various tramping modes and different names given to the different vibration modes. In aircraft we have wing torsion, we have wing bending, and you have fuselage bending, fuselage torsion, and so on. Constructing a figure such as we've done here is important, and these are quite often used in study of flutter of aircraft. So you want to watch for the frequency crossings, partly to not lose your understanding of the system at some high change situation, and then also because of the danger, especially when there's an energy source somewhere, of having a flutter-like instability. Let me start with a discussion of a component of this device, namely the armature arm housing. We can take another brief look here just to remind you of the piece that we're speaking of. It's this swinging arm that's kind of the key to the tracking on the particular circle of information that you need. Well, we'd like to raise the natural frequencies of that arm. Basically, it's here's an older design shown here, and this arm pivots on a shaft shown here with the light green line. The arm is about 5 inches long and roughly 1 3/16 inches wide, 1/2 inch deep. It's controlled by rotation about this shaft, and so there's really only 1 degree of freedom in the problem. I think of that particular motion as rigid body rotation in that the body is fairly stiff in that plane, and you're hoping just to center it on the particular information track of interest. And you'd like that to happen without a lot of distortion in the arm. Now the arm will slew at some probably moderate frequency, so you are going to whip it around a little bit, and if the arm were very flexible in that plane, then you'd be in trouble. This particular part of the total project on the armature arm was carried out by a graduate student. He was available during the summer and I wanted to go on vacation, so I put it in his lap and gave him a month to do the job. Hopefully it was to have been done with 1,000 degrees of freedom, and then it would have fit into a larger system model of about 5,000 degrees of freedom. To my surprise, when I came back from vacation, he'd actually used many, many more degrees of freedom than that and made the problem too difficult so that it didn't really have a chance to be a part of a larger system with the computing capacity that I had allowable at that time. So from that standpoint, it was a little bit of a bust in terms of the relevance for the system model, but we learned so much as a component that that carried forward. The first thing that I do on a project like this is to do the physical modeling, and then I follow that with finite element modeling. So physically the question is that little arm, is it a linear elastic situation? Well, yeah, the material is aluminum, although later on it was made out of magnesium. We do use small deflection theory, and that's appropriate because you're moving this read-write arm through relatively small motions, although quickly moving it around. On this particular sub-problem, I did assume that the shaft was rigid. So we were looking more or less at the vibration properties of the elastic arm and not the mounting system which held it in place. The so-called rigid body rotation of the arm about its axis was restrained by a spring, a weak spring. And I did that much in the way that experimentalists do when they like to have a body not drift off into space, and they mount it on weak springs. There also was, at the time I did this, some problem with some of the methods on getting zero frequencies. And so it was a common practice to put a very weak centering spring to hold your body in position. And then that gave very low frequencies of a couple hertz for that kind of motion. I really wanted to know about frequencies below 2,000 hertz, thinking that then I would understand the problem pretty well, and I might want to understand the first 10 natural frequencies. There were fewer than 10 below 2,000 hertz. In fact, I went on up, as you'll see on the next figure, to some 7,000 hertz, looking at the frequencies. This was a biggie, though, to model as a solid rather than a plate structure. It would have saved a lot of degrees of freedom to have only modeled that casting as a set of plates. The little sections were pretty thin compared with their planned dimensions, except for the relatively rigid hub of that read-write arm. Now, I might have had to have the hub still modeled as a solid, but then have the little plates embedded into it, the little plates that made up the arm itself. Were I to do it over again, I believe I would treat that as a plate model. I did include lightning holes, and there was quite a bit of cutout material, so it made really a dominating difference on the design. I decided not to include the Winchester head because that was going to be common to all of our studies, and I was trying to optimize the read-write arm as well as the other parts of the casting, motors, and so on. So I thought I would leave that out. I did want to put in, though, a relatively heavy armature and sensing pair of coils in the base of the armature arm. They both drove the arm and then sensed where it was positioned. Now let's talk about the details of the finite element modeling. I use the MSc Nastran finite element code for this study. We use solid elements, we use the hexa element, 20 noted elements. That was probably overkill. Our model ended up with way too many degrees of freedom the first time it was done. An interesting thing was that I made a foam model out of polyurethane foam, and by cutting out the holes in the proper places, we found that it was really a bad design. When you picked it up, it literally folded about a certain hinge line that I'll point out in the next figure. So I gained some respect for making some simple models of things. Had they done the original design with that in mind, they would have realized how weak this particular design was in respect to this particular kind of a deformation. Now, you might think of that as a strength problem, but we're worried about stiffness. So if it collapsed that easily about some hinge line, it probably was relatively weak in flexural bending, in vibration also about that hinge line. Now, we want to keep the degrees of freedom below 1,000 so that this can fit into a larger system model. The spring stiffness to restrain the rotational mode I would like to be so weak that your rotational frequency would be far less than the first elastic frequency. I use the inverse power method of solution from 0 to 7,000 hertz. That would have given me my zero frequencies had I not used the spring up above, and so I think my use of the spring was a little bit of an artifice and not really needed, particularly nowadays. Well, the results that came out after the solution did identify the normal modes of the system. I wasn't very surprised about the rigid rotation about the shaft because we knew that was controlled with just a soft spring and it's a very low frequency of a couple hertz. Then the lowest mode, the lowest real elastic mode, was a bending mode. Then there was one that I called spreading, in which the two surfaces, the upper and the lower surface of the arm, vibrated out of phase. Then there was a kind of a torsional mode, and then on up. So you can see I'm naming my modes here like Elmer and Fred and George. Now let me show you the finite element mesh that we used on this baseline model. The original armature arm shown here has these rather large lightning holes. When I made the foam model, it showed immediately that this was a poor design in that along this axis here, the outer arms would just collapse. So the lightning hole tended to undercut the what would amount to the root of a cantilever beam here. There was one post located in this body out in here, and that held the surfaces together a bit. The micro Winchester heads were located on two springs that came from the tip of the armature arm out here, and then they projected out over the spinning disc. The disc itself then had to clear this arm and came through in an arc, something like this. Actually, the amount of the total surface area that was written on was not dominant. I think it was probably half or so of the disc area, so there's a lot of waste magnetic space there toward the outer rim and toward the hub of the spinning disc. The rigid shaft went through this point. Here is a gap where the coil of the armature was embedded in epoxy, and I did model that, both the mass of the copper wire and the epoxy. There was a small sensing coil at this location that would tell where the armature arm was at any instant of time. That was found to be misplaced and interfered, or was interfered with, the armature coil, and so they later moved that smaller coil to the other side of the deck of the casting, the main floor of the casting, to protect the sensing coil. Well, after running the modal analysis, we came up with the first rigid body mode as expected here, with the displacement shown in red. There was a small spring that was connected so as to give this some very low frequency. There was no elastic deformation to speak of except in the small. The second and third modes were indeed elastic modes, shown here. Because of the post at this location, the upper and lower surfaces of the armature arm had to move together, but the outer parts of that arm were free to move either in synchronization as shown in the top figure or out of synchronization as shown below. In both cases, when I showed these figures to the electrical engineers, they gasped, "Oh no, the arms are hitting each other, you know, you can't have that." Well, of course, now that we're experienced structural mechanics people here, structural dynamicists, we know that these motions really are infinitesimal and that the plotting package of the computer just enhances those infinitesimal displacements until they're large enough for us to see. Many plot packages will make the largest deformation perhaps 10% of the total figure size. So this gets your attention, that's for sure. The frequencies 692 and 1031 are pretty low considering that we want the entire assembled system to have a frequency above 500 hertz, and there's a lot of flexibility here just in these two modes. Some of the higher modes for this arm have substantial motion of this tail of the arm back where the coils are. It's relatively massive considering the total system and that this is a pretty small system. And this tail would kind of flap up and down. I think I had one that I called a tail flap mode. That wouldn't bother too much in the sense that you're trying to track the location of the Winchester heads out at the tip, and so provided the outboard part of this arm was reasonably well behaved, you might not even care if the tail would flap around. So it's good to get a physical interpretation for what these elastic modes are. Perhaps you can live with some and not with others. One thing that is true is that the bending problem shown here is not really that disastrous in the sense that if you've seen a vinyl phonograph record played on a conventional phonograph, you notice the needle can ride up and down in the vertical direction if there's any warpage of the disc. On the other hand, side-to-side slewing motion would be a disaster. These Winchester heads have a little bit of that same characteristic in that they're spring-loaded in the vertical direction, and they can move in that direction without losing acquisition of the track. But again, the slewing direction would be the one that would be a bad kind of motion if it were elastically coupled into the modes of this armature arm. There were a total of 3 finite element frequency runs made. The first 2 had to do with the baseline design and then a modified baseline design where 2 more posts were added between the upper and lower surfaces of the arm. The third study had to do with a complete redesign where John Taylor helped lay out a Virendale truss and was able to lighten the structure and make it look prettier as well. You probably remember my saying that this model with 4,800 degrees of freedom was too complicated for the final system model, but it was easy to modify and add a couple posts outboard to give us a second run. The third run shown here came in under 1,000 degrees of freedom as I had desired, and this was another graduate student, Kim, who did this particular job and did a nice job on that. Now, if the difference in design 1 and design 2 had to do with adding posts outboard, then it turns out that has no effect on the rigid body rotation on the rigid shaft. Neither did the redesign later. But those outboard posts did stiffen the first bending mode. That could be expected because you would have a shear coupling then between the top and bottom fibers of something acting in a beam-like manner. But the spreading mode was really greatly affected because those outboard posts prevented the spreading mode from happening at any reasonably low frequency at all. Now, it wouldn't make this frequency go to infinity. It would just make it up in tens of thousands of hertz. If you made me guess, I might have seen that somewhere around 20,000 hertz. I think at one time I located what that, where that frequency had moved to. The torsional mode was one that I didn't show in our earlier figures of the mode shapes. It too is stiffened by adding outboard posts. The later design, the redesign as a Vierendeel truss was here, and you can see there's quite a bit of help now on the first bending mode, moving up to 1028 Hertz as opposed to 692. And in my mind, this was a good goal, was to get all the components up above 1000 Hertz, hoping then that the assembled system would be above 500 Hertz. After these studies on the armature arm, we made a few conclusions. One was that you needed to have posts outboard on the armature arm. That somewhat conflicted with the requirement for getting the disc to pass between those two portions of the arm, but turned out not to be a big problem. Still, the armature arm wrapped around the disc in the extreme position as shown, but that all worked out fine. We reshaped the whole pattern, made the armature arm substantially lighter. We tapered the cross section shown here. There wasn't as much need for material out at these free edges, and material there tends to add more mass than it does stiffness to the total armature arm, so better to lighten that up. The people at Irwin International were quite happy with the redesigned armature arm, and it was ultimately made out of magnesium. After completing the armature arm problem, then I was asked to do the mainframe normal modes. This was a single-piece aluminum casting. One problem is that you're not allowed with a casting to have sections that are thinner than a certain amount because of possible cracking. In this case, and at the time we were doing this, 90 thousandths of an inch thick was what they wanted to maintain. That's a little bit heavy. I'm sure they do better than that nowadays. 90 thousandths would be a little over 2 millimeters. Here's the casting. It's the same one that I've shown you the actual model of. It's aluminum, thin-walled, has a lot of reinforcing ribs, but the natural frequencies were too low. They were 318 Hertz and 478 Hertz as we calculated them and measured them. We were afraid that vibration at those lower frequencies might couple in with the rotational rates here and harmonics of that, the way the ball bearings would move around in the races. The rotation speed was about 3,000 RPM or about 50 Hertz at that time. So that 50 Hertz dominant motion is kind of the driveline motion of the system, and then depending how your bearings act, you can, if there's some nonlinear excitation there, you might get so-called superharmonics up at 100 Hertz, 150, 200, and so on. It was felt that if we could stiffen this casting and raise all natural frequencies above 500 Hertz, we would be okay. I did the model on this mainframe casting myself. Probably there wasn't a student available to do the dirty work, so I got in and pitched in. I modeled it as a stiffened plate structure. I assume small deflections, very reasonable thing to do, and that the material is linear and elastic. I was interested in frequencies below 2,000 Hertz, at least to clear out what all those were. Again, I used the trick as an experimentalist would of supporting the casting on soft springs so that it wouldn't have the zero frequencies for the 6 rigid body modes. That's not really necessary in our theories nowadays, although you see we did actually do some of the experiments that way, and to some extent that made sense. The finite element modeling made use of quad 4 plate elements and bar elements, which are compact beam elements. I was able to keep the degrees of freedom just below 1,000. I used inverse power, and I actually searched up through 3,000 hertz for frequencies. The lowest two elastic modes were of great interest to Irwin International. They came in at 318 hertz and 478, both in the danger region. The lower one, as you might expect after you think about it a little, is a twisting mode, and I'll view it from the open end of the casting as shown. The far end might have, for instance, this green deformation pattern, and the near end might have this blue pattern. This is a little bit like the vibration of a thin-walled, open cross-section beam, and you know that that is a particularly flexible kind of motion for open section beams. So it kind of makes sense. It's sort of a torsional motion. Then the cylindrical bending is shown here, where the walls alternately flop outward and inward, and that happens along the length of the casting, so I'm calling it cylindrical in the general sense. It's a general cylinder shape. 478 hertz, still in the bad region. So we did confirm the two frequencies that had been picked up by the fast Fourier transform methods, and our answers were not very far from the true experimental values. It was 5 or 10 hertz off, or even less. So it was an excellent confirmation of what had been picked up experimentally. Now, to help them on this design, we decided to stiffen up, especially on the open ends at the floor, with some stiffeners. We tried to stiffen the floor and the motor well to help a bit there. And a big change that we decided was to convert from a cover that was over the spinning disc that originally was kind of a cosmetic cover, just to clear plastic and just kind of a simple non-structural member, over to a true aluminum strong stiff cover that used a labyrinth seal with an O-ring to actually make a dust tight connection, but then was bolted down so as to provide a hard metal connection and give some stiffness to the structure. So it really helped, especially on that torsional mode, to keep the body from having these low frequencies. After doing those two major components and seeing how to stiffen them up separately, we decided to put the system together. And this assembly was going to include the rotating parts of the disc and the with its hub, with the spindle and the motor underneath, as well as the armature arm and its shaft, and then the mainframe casting. We also put the cover on and made it an integral primary part of the structure. So we wanted to find the normal modes for this assembly now. There would be some zero frequencies possible. You might think of the rotations of both the spinning disc and the armature arm as mechanisms. In a static problem that would doom you, but in a dynamics problem you can have that. So in addition to those two modes, there would be the 6 rigid body modes of the total system. As I did for the components, though, I restrained those with soft springs so that rather than having 8 frequencies at 0 hertz, I had frequencies down at a couple hertz for those modes. In my physical modeling, I decided not to use any representation of the circuit boards internally or the air filter. These bodies inside would add both mass and stiffness, and they weren't available at the time, and they were changing rapidly, so I thought it was better not to get into that. So I basically optimized the system in terms of its primary structure and not so much on this secondary, and wanted to find out what the frequencies below 3,000 hertz were. Here's a figure showing the cover and a top view, and you can see the bolt holes where it's now bolted at a number of places around the periphery. Turning that into primary structure took a little bit more work than just a decorative cover. They did decide that they didn't need to see into the spinning disc, and this was going to be out of sight anyway inside a computer, so they didn't regret that decision at all. The finite element model of the assembly was actually very straightforward. I had some help from another student, Dave Seidel, who's now at NASA, and he did the rotating disc, the hub, and the spindle, and the motor. Here you can see the soft springs that I used to restrain the mechanisms involved in the armature arm and the spinning disc. You might ask whether a spinning disc wouldn't affect the modes of vibration, and there could be a coupling there. You could have the gyroscopic effects. That's an energy conserving concept and wouldn't add energy to the system, but in fact could do some kind of coupling between the modes. We neglected that in any event and decided we would assemble all of our components together. We had some solids in the armature arm and a lot of plates and beams in the other portions. The ball bearings in the bearing wells were modeled not as real structures, but rather as spiders. In other words, with some radial stiffnesses that set the shaft and the spindle off from the walls of the housing. These stiffnesses were given to us by a Japanese ball bearing company that was going to provide the bearings for this system, and they were really good about giving technical data, and they had measured values for the stiffnesses of their ball bearings. Typically the shaft would be in this case vertical, with the mainframe casting having a kind of a well here. It actually looked like a hollow tree stump, and then your ball bearings would be located in a race at one end of the shaft or the spindle as well as the other end. So the shaft then was confined between these two ball bearings and then had something happening out at this other end, either the armature arm or the spinning disc. All told, our model had 3,064 degrees of freedom with some 500 elements and 900 grids. Here's the mesh for the system. Because I'm using this stick model, or sometimes called wireframe model, without any hidden line removal, you can get the always obnoxious optical illusion, which will make this picture alternately flip with the walls going away from you or toward you. I seem to have an easier view with this wall projecting toward me right now, so I'll view it as that way. Here's the armature arm then, which would be actually on the far side under that viewpoint, with the well here for the shaft. The motor and the spindle would be here with a spindle protruding through the floor of the casting, the mainframe casting. The rotating disc is shown here, a rather simple model with only some 8 segments around the periphery. The cover is shown on the what would, in my view of this image, is at the bottom of the disk drive. So I'm looking at this from the underside, basically, where the two walls to me are pointing up out of the page toward me. So this is a system, and we're interested in how this behaves. We're interested in the natural frequencies and mode shapes. The main idea is how flexible is this arm and how well can it track the concentric circles that are written on this disc. I tried to visualize what was going on here and thought that maybe tracing out a flexibility path would be a good way to think of this. In this figure, I'm tracking that a source of error then would be the relative displacement between the tip of this arm and the relevant track here on the disc. Well, that involves the flexibility really down the Winchester head, through the outer part of this armature arm, through the base of the armature arm, into the shaft over here, into the flexibility of the ball bearing, into the bearing well, into the floor of the mainframe casting, into the other bearing well, through the bearings, through the spindle, through the hub, and ultimately out on the disc. So that if this is vibrating either in a slewing direction or vertically, then it's going to cause problems in tracking here. Interestingly, at the time we were doing this, we were trying to track on information that was spaced 1/1000th of an inch apart, but at that time there was a Japanese laboratory that was doing compact discs, as I believe, in retrospect, and they were putting down tracks that were 12 millionths of an inch apart, and with a, I think that was like a 10 millionth of an inch track with a 2 millionth of an inch gap between the tracks. In any event, I know in metric it's hard for people to figure that out easily, but there's a fact they were doing in a laboratory setting with air-bearing spindles. They were tracking 80 times more accurately as we were, and to do that they had to have not only electrical control at the root of this arm, but they also had another spot here like a wrist with another pivot, and they could do vernier corrections on the gross motion of the body. And that was a laboratory situation where I imagine this was a $100,000 device that I'm describing now, whereas the one that we were trying to develop here was to have been $500 or less. So certainly how much you can accomplish has to do a bit with the budget that you have. Now, I remembered also that during summer trips with my family, that we often got into a situation with 3 little kids in the back seat that they would get thirsty and want to drink, and then my wife might be sitting in the passenger seat in the front and would grab say a half gallon of water and lean over the front seat and try to pour water into a cup being held by a child in the back seat. And you can about imagine how that goes. It would be very similar to this, that the flexibility of the entire automobile through the through my wife's arms and down into the seat, bouncing around in the body of the car and into the back seat, and with the kid finally holding the cup, and you got all this jiggling and joggling. You can see that there is a total flexibility path there that makes it hard to position something precisely. I'll show 3 figures for the mode shapes on this total system and then give a table with some more frequencies as well. The first mode of this system is characterized by bending of the spindle here on which the disc is spinning, and you have the relatively heavy magnetic material that forms the motor. The bearing well, you can see, is tilting as well. Now, this is, of course, again, an exaggerated motion, and nevertheless, though, you're seeing where the dominant flexibility is. The spindle was about a 1/4 inch steel rod, and so that wasn't exactly a weak namby-pamby structure, but yet relative to the weight that it's being asked to carry here, and I should discuss it in terms of mass, this mode is the lowest mode. Now look how the disc is going up and down on this. And again, when I showed pictures of this to my electrical engineering acquaintances, they were worried about this. My gosh, the disc is going outside of the chamber that it's supposed to be spinning in. And look, the read-write arm is going the other way. Well, those are important relative positions, but the amplitudes are not important because that's not scaled, as we've discussed a number of times. But this would require some flexibility then in the Winchester head then, because as with the vinyl disc on an older phonograph, you would need some vertical play here to keep tracking the same circle of data. But we are happy that this is above 500 hertz, and so our lowest frequency in the system was acceptable. The second elastic mode is similar to the first in the sense that it's primarily a bending of the spindle, but it takes place in a plane that's orthogonal to the first elastic mode. In this view, it doesn't show up so well. You can see what's happening, though, because the disc is tipping in a different plane, and we see the flat of it here. Again, though, the read-write arm is moving upward here, and at that point, the disc is not moving as much. So this is definitely a motion in a perpendicular direction from the first bending of the shaft. See how the motor itself is being tilted here, the magnet that makes up the motor. The third elastic frequency of the system is largely an armature arm flapping, shown here. And again, I had to calm down my electrical engineering friends and tell them, no, it's not really flapping outside of the disc chamber. We're getting a little bit of motion of the cover of the chamber as well, which was interesting. About the only time that we got anything going on with the cover. So it's interesting to look at the mode shapes and see how it might affect the tracking of the system. Again, the frequency above 500 hertz, so we're in pretty good shape now, and I'll tabulate these in the next figure. Here I'll show the tabulation of frequencies with some names about mode shapes. We show two different studies for the assembly. One was the assembly without the cover, and the other is assembly with the cover. We also can hearken back to the mainframe solution standing alone. When you add the gear onto the main frame consisting of the armature arm and the spindle with the motor and disc on it, you actually lower the system frequency. And that was what we had expected initially, that the assembly would have lower frequencies than the components individually. But when you put the cover on, then you stiffen it up quite a bit. So that cover really was helpful and brought us into the safe region. Likewise with this higher mode here, as we put on the armature arm and the spindle with its motor and disc, we got this frequency at 303. These are relatively close because the real source of flexibility here is in the spindle, not in what the sidewall is doing. Finally, if you put on the cover, it raises that second frequency nicely as well. The third frequency, which we thought of as an arm flap here, was up a bit higher initially and then was raised nicely by the stiffening of the cover. There really is an open question about the mode tracking. I can really not guarantee you that this twisting mode really is an integral part of this particular action and not this. you'd have to make minor parameter changes, and this was an enormous change in the system. So the logic is a little bit weak on my mode tracking from this number to this one and this one to this one. I think there would be a lot of blending of the mode content of these two into both of these behaviors. But that could be unscrambled if you could do some sort of a gradual assembly, put on one little component at a time. Interestingly, though, we did pick up the disk bending modes. They occur down here at 748 Hertz and 750. The only difference being the slight amount of non-symmetry between the fore and aft and the side-to-side vibration. That would be because the sidewalls would add a little more stiffening compared with the open ends of the system. Unfortunately, the attempt to come out with the first mass-produced disk drive for PCs failed. Irwin International went bankrupt, and the surviving effort in that entire project turned out to be the relatively fast tape recorder that was put in it, and the tape drive could record the entire amount of information on that disk in just a short time. I think the number at the time was 2 minutes for the 5 megabytes. Now those rates are not high in today's market, so this was certainly an early attempt, but a very good attempt. It also reminds us, though, that even though you work hard on the engineering side, you also have to do a good job on the manufacturing side. And I heard critics of this project predict the failure because of manufacturing right from the outset. From the day I walked in to help these fellows as little as I could, there were other computer people in town that were saying that they'd never be able to make it. And that did turn out, apparently. But what a noble try, and had they succeeded, they would have been an enormous company by now. You've seen other disk drive companies that made it and are just enormous companies now. So what a good try at making one of the first compact disk drives. If I understand right, the problem in production was that they were getting flaking off of the aluminum castings that would get onto the disk, and that they tried new materials in the read-write heads, in the Winchester heads, that also contaminated the disk. The particular model that I have in front of me, when it was initialized, apparently scraped off, because of so many crashes, scraped off the magnetic media over the bulk of the surface. And so the model I have here was one of the ones that was unfortunately not able to make it into production and couldn't even make it through test. Well, I did use this particular study, though, as a motivation for some of my own doctoral students. Kyuk Kim and Curtis Hoff were two doctoral students who used the mainframe casting as a model for trying to work out what we call nonlinear optimization through perturbation methods. I challenged each of them to raise the natural frequencies of the mainframe casting to 500 Hertz or higher, the same challenge that we had had earlier. This time, though, not by adding a cover or adding small stiffeners, but rather by changing the thickness of the casting in the different regions. In the next figure, you're going to see the results where it shows changes that are substantial, above 30% changes. That was a good workout for our nonlinear perturbation methods, where we carried higher order terms that are neglected even today in optimization, even though it's becoming a fashionable thing to do with linear sensitivities. We actually were ahead some time ago on how to do this, but never commercialized the process. People involved were myself, Sandstrom, Bernitsis, a faculty member in Naval Architecture, Kim, and Hoff. National Science Foundation put some money into this at the outset, didn't want to put money in later to commercialize it, and probably that's consistent with their general goals. We came out with 3 AIAA journal papers and were able to show these results in a kind of a nice, concise way. This final figure shows some of the thickness changes that were prescribed by the method that Kurt Hoff used. We asked for a plus 34% change here in the floor at that point, 48% increase on the floor here around the armature arm bearing well. There was a 25% change in the thickness of a stiffener here. But there were some reductions in thickness on the side walls. Kurt and Keough both did a kind of study here where they not only maximized the stiffness of this body, but they also minimized the weight. And so they were able to gain that added frequency and actually reduce the weight a bit. So it's an example then of the kind of optimization that's being done now more and more, where you have constraints such as our frequency constraint to be higher than 500 hertz, and then you have an objective which is perhaps in this case to minimize weight. So that's the end of our case study.